through 10. 7 through 10. We're going to attempt to do some matching. And there are a number of ways to do this matching. I want you to notice a couple things about the matching. What we are doing is we're taking slope field graphs, and we'll be attempting to match those slope fields with differential equations. Notice that all of your options down here, 7, 8, 9, and 10, all of them are differential equations. Dy dx equals whatever. And so because of that, we can look for those patterns that we talked about earlier. For example, let's take a look at A. See if we can match A up somewhere, 7 to 10. On A, do you see a horizontal pattern or vertical pattern or neither?
Horizontal.
Horizontal. So if you have a horizontal pattern, that means the slope only depends on what? What? It only depends on y. So as we look through there, I would say that A will not be 7, right? A will not be 8. And A won't be 10 either, right? So I think that A has to be matched up with 9.
Will it always be like multiple choice, or will we actually have to write?
Both.
Okay.
Potentially both. Okay, so that one was pretty straightforward. What if you didn't see it? What if you didn't see the patterns as easily? What could you do? You could plug some points in, right? Just in a sense, create a table. So what I'm seeing here, like a really key point that distinguishes this, is this, this line of horizontal slopes right there. It should be showing up. There it is. So that line of horizontal slopes, doesn't that appear to be at roughly y equals 2? So the idea is if you plug in y equals 2, you should get 0. And I think 9 is the only one that works with that, right? I mean, 7 or 8, you get x minus 2 or sine of x, it makes no sense. And so you start plugging some points in, making comparisons. You should be able to pick them up. Okay, let's take a look at B. What kind of pattern do you see on B? Horizontal, vertical, or neither? So that means dy dx should only depend on x.
Which could be either
7 or 8 or 9. So that idea really didn't help us in the slightest, did it?
Well, no. It's
so we need to get a little deeper there, right?
Because
oh, not 8, sorry.
Yeah.
Yeah, my bad. 7 or 10. 7 or 10, because 8 has the y in there also. So that helped us, but it certainly didn't give us the answer as easily as number 9 did. So then how do you think you can make a distinction between 7 and 10 as compared to matching it up with B?
or as
You can see kind of a parabola-looking shape. Yep, agreed. I mean,
well, actually, it would
like that, I guess.
like if there were x and twin, it would just be like a cross slope 1, slope 2, slope 3.
I'm not sure what you're saying.
Because when x equals 1, as you like go
Okay.
around, so it would have to be like just increasing in the slightest.
Yeah.
So
I love that. You see the pattern that Andrew's talking about? If you start at the origin and go right, can you see how the slopes increase? It goes from like a positive slope to a steeper positive slope to a steeper positive slope. And out there on the right, it's getting close to vertical, right? So in other words, as the x values increase, the slope increases accordingly, right? What do you see with C? Like, what kind of a pattern do you see with C? Say it again? It's cyclical, right? It goes up and down. So, like, if we kind of do B and C together here, isn't it pretty clear that 7 has to be matched with C, and 10 has to be matched with B? I mean, even though they both fit the idea that, both of those slope fields only depend on X, therefore you get the vertical pattern, the cyclical nature of C and then the non-cyclical nature of B helps you distinguish between them. And my computer is really super duper accurate. So maybe, no, we can't do that. So I need to record the video. We'll just have to deal with it. Okay, and then of course that leaves number 8, doesn't it? So 8 has to be D. Well, let's talk about how this works. Do you see how 8 the slope depends on both x and y. And so you're not going to get a vertical or horizontal pattern. It's going to be that kind of twisted, diagonal, that kind of thing. So number 8 has to be D. And we actually did a slope field really similar to D. So
Are all X and Y, where it has both of them, are they all diagonal? Because this one
it's going to be twisted in some way.
okay.
I don't know if I would say they're all going to be diagonal. I can think of one that doesn't really take this diagonal look, but it's kind of twisted, I guess. Let's do this. Let's give you all a chance to do this by yourselves. Let's try 11 through 14. See if you can match these up. Do it again. All right. So what did you guys match up A with? Which number did A go to?
14.
Oh, we had disagreement. I love it. So I'm hearing A going to both 13 and 14. So let's skip that one. What do you guys think about B?
11.
Why did you pick 11?
Because it goes vertically, which would mean that at every X value it equals that.
It?
The dy dx is the same.
Sure. I think 11D, see the vertical pattern. 11 is the only one where the slope only depends on X. Okay, so we took care of B. How about C? What do you think for that one? 12, everybody? Yeah, I agree. I think 12 and C match up. So it's going to come down to 13 and 14 matching with either A or D. Right? Okay. So can anybody present their case? Like why you think it is whatever you think it is?
On A,
Yeah.
I think that it's X plus Y because when you have 1 negative 1, that equals 0. When you have, which would mean that like it would be 1 minus 1 in that equation. And if you have 2 negative 2, that equals 0. Then
So
also,
you're looking at that point right there,
yeah.
sort of, and then this point down there.
And then also, if you're keeping X constant,
Yeah.
as you go up, you're adding 1 Y value, and it's getting increasingly more C as you go up.
I like it. You hear what you just said? If X is held constant, as you move up on the Y's, the slope should get more positive. Right? Anybody have a contrary argument? Or was he the one that came around? And I thought somebody said 13 was A or something like that. Maybe I'm misreading. Yeah, so I think 14 definitely is A. Okay, and then 13. 13 and D obviously go together. What kind of solution curve do you see for D? I think you would actually sketch the function. A circle, right? We've got these concentric circles. So what do you think tells us how big the radius should be? Like what part? I don't know if we talked about this now. Let me show you this. Check this out. I want to solve D for you. So 13. So dy dx is equal to negative x over y. Remember when you solve these differential equations, the first step is to separate the variables. So what would that look like here? If the variables all by themselves. So the x is on one side, y is on the other side. Okay, so algebra. Any thoughts? How do you get that? Micah really the only one that did that? No? Yeah. You did too? Okay. Okay, good. Okay, so if you remember, once you've separated the variables, what's the next step? We gotta get rid of those differentials. Right, integrate both sides. So we're gonna get 1/2 y squared equals -1/2 x squared plus c. Okay, now let's get this into a more recognizable form. And you can see from the slope field that the solution curve should be a circle, right? So how do we make this thing look like a circle?
Add the half x squared on the other side, and then it's in standard circle.
You can take it a little bit further, right? Couldn't we multiply by 2? So y squared plus x squared is equal to 2c. What does the c stand for? Oh, well, let's talk about that.
C is equal to r squared.
Like the plus c over here? Understand, it's a good question. The reason is, you know, like if you have a plus c on the left and a plus c on the right, it appears that they would add out, right? Subtract c from both sides. That seems like the c's have disappeared. But the point here is that you can have any constant added to either side, right? So to say plus c and plus c almost makes it seem like they add out, so there isn't one, but there is one. So maybe you could do this. You could say this is like c1 and this is c2, right? Well, let's say you did subtract c1 from both sides. What would c2 minus c1?
The difference.
The difference of two constants of which neither you know. So the result would be another constant.
Yeah.
So we'll just put the constant on the right side. That makes sense?
Okay.
So no, I don't put both of them. What I do is this, is I would say, yeah, essentially I would say that this c, that c right there would represent the difference between the two constants, but it doesn't change how we do the problem. But, yeah, you're right. Technically that's kind of what's going on there. And so along those lines, let me ask you this. So here's this c that we're just working with. Does anybody know what that c is?
R squared.
Well, don't go that far yet. Does anybody specifically know the number for c?
In terms of answers?
No, just like 10, 29, 52.
No.
Nobody knows what that c is, right? So 2 times an unknown constant is simply some other constant. And so really, you could just certainly justify yourself in saying, yeah. There's some technical notation, you know, you might be forced to make if you took a college calculus course or something like that. But really, practically speaking, it's simply equal to some other constant. And then Andrew's point about c being what?
R squared.
R squared is certainly valid. So whatever c is going to be the radius squared. So then you can figure out if you have a really big circle, a small circle, a medium circle. Questions? All right, sweet. All right, got one more matching for you. And it's already been done. Close your eyes. Close your eyes so you can experience it on your own. Sorry. No. Okay. Here we go. Left over from my other class. So take a look at this one. Can you tell me on number 15, how is 15 different from the previous 2 matching sections?
X is held constant. All of the answers have X being held constant.
I would agree with that. Yes, that is a difference. There's another difference. True. Very true. There it is. That's the biggest difference. I'm asking you to compare the slope field not to dy dx, but to y.
Yeah.
To the actual function. So this is one of those scenarios that if you are really good with graphs, like if you're good with matching graphs to functions, it's going to be pretty easy. Yeah, if you're not so well versed in matching graphs to functions, we're going to have to do some work. Okay? So let's assume that we all need to do a little bit of work. And here's what I suggest. If you're looking at this and you're looking at that slope field and you're like, I have no idea what that matches up to, here's what I suggest you do. turn each of those y equals, each of those functions, turn them into differential equations. So how do you turn a function in terms of y into a differential equation? Take the derivative, yeah. So a would be dy dx equals 2x. So let's just stop right there. Let's see if we can get a little comparison going and see if we can decide if A is the correct answer. Take a look at the slopes. So this is 3 out here. So let's say that 2 is about here and 1 is about there. There we go.
No, it couldn't be because they would have to be getting steeper instead they're actually getting more
Andrew
horizontal.
has identified a really good pattern. Will you say that one more time?
If it were 2x, then they would, as you go across the x axis, they would be getting steeper, but they're actually getting more horizontal.
Does that make sense? Yeah, well said. Very well said. So I'd say A is pretty obviously out. B, what's dy dx for B?
Yeah.
E to the x. Yep. Okay, so any thoughts on that? Is e to the x a possibility? Why? Right. It's kind of a similar idea to what Andrew just said, isn't it? Like if dy dx equals e to the x really was the differential equation that matches this, as you go from left to right, shouldn't the slopes be increasing? I mean, think about it, e to the first, e to the 2, e to the 3. The slope should be getting steeper and steeper and steeper, but instead they're getting flatter and flatter. They're still positive slopes, but they're getting flatter, they're getting less positive. So I'd say B is out. C, what's dy dx for C?
E to the, or negative e.
So the negative x. So I want you to think about this one. This gets into like functions and how these things work. If you take e to any power, just e, any power, positive, negative, big, small, whatever, what comes out? E to any power, anything you can possibly think of. What kind of number comes out? Positive.
Yeah.
Right? So then if you slap a negative on the front of something that's always positive, the final output will always be negative. So in other words, if C were the correct answer, wouldn't all of these slopes up here have to be negative?
Yeah, we're sure.
Which they are. They're all positive. Now they're decreasing, yes, but they're all positives. Okay, how about D? What's your instinct tell you on D?
Now we can do the deal waving.
You need some kind of cyclical pattern, right? Yeah, so I would say that yeah, D is definitely out based on that. So that only leaves us with E. So what's dy dx for E? 1 over x. So hopefully this makes sense. Think this through. As x gets bigger and bigger and bigger, don't the slopes seem to get less steep? That really makes sense with a fraction, doesn't it?
Yep.
If you think about it, 1 over 1, and then you go to 1 over 2, that's going to be half as steep. And then you go to 1 over 3 for your slope, that's going to be even less steep. Still going to be positive slope. That's going to be getting less and less steep as you go from left to right. So let me just get a quick poll from you guys. How many of you looked at that slope field and saw ln of x? Anybody?
I didn't see ln of x, but I see 1 over x. What?
You see the slopes
Yeah.
doing 1 over x?
Yeah.
Definitely. So what I'm saying is this. Graph of ln of x looks like that. Can you see how that matches the slope field pretty well? So that's why I say, like, if you're really familiar and really skilled at seeing graphs of functions and matching them with their function, then a scenario like this is going to be pretty quick. You're just going to look at it and be like, does that look like the graph? No. I mean, here's what you could do. You could say, you know, A is a parabola. Does that match? Nope. B is e to the x. And I think this is kind of what Micah was saying, I think, a little bit. Here's e to the x. That doesn't match. It's going the wrong way. E to the negative x looks like this. So that's completely wrong. Cosine does this. that doesn't make any sense either, right? So ln of x would be the one that actually seems to follow that slope curve pretty well. Good? Man, we're doing excellent on time. I like this. We're going to leave slope fields alone. And I'm going to do something really cool. Okay, so now we don't have to mess with our other classic stuff. So guys, we are going to, for now, skip 17 and 18. I think we'll probably treat those like review problems when it comes to quest time. So let's just skip those for now. And let's move on to 6.2. I really like 6.2. 6.2 gets pretty nitty-gritty, detailed, and practical. But before we get into some of the practical stuff, I want you guys to practice what we've done before with differential equations, and that is to solve for the general solution. So let's take number 1 here for a second, and if you would, let's rewrite y prime. I'm not a big fan of just writing y prime in this situation. What is Leibniz's notation for y prime? Yeah, so let's do that. Let's go dy dx equals 2x over y. And I just want to turn you guys loose for just a minute. See if you can separate the variables and then solve for the general solution. All right, so Victoria, how did you separate the variables? How did that look?
So I got y dy 2x.
I agree, that's good. Any questions? Sam, what comes next?
And break, and then I got 1/2 y squared equals x squared plus c.
Very good. And then if we're going to take it to the general solution, we can solve for y. So multiply by 2, and then square root both sides, you're going to get plus or minus the square root of 2x squared, and I'm just going to put plus c. Understand that that's 2c, but remember, if c is an unknown constant, then 2c is also an unknown constant. So it's c. All right. Any questions? Awesome. All right. So let's
Wait,
talk.
why didn't you
I'm
do-
sorry.
You started out with 2x, so why didn't you do 1/2 x squared?
We did.
You did x squared.
So let's do it like this. Right?
Oh,
You get 2 times 1/2 x squared.
okay.
So you just get x squared. Good question. I definitely need to figure that out. Anybody else? All right, cool. All right, exponential growth in decay. Have you guys ever seen that? Science class, maybe? Anybody ever seen that in physics? Pre-calculus? Maybe chemistry certainly could agree there. In physics, it would be like electricity. If you're doing electricity, I know it shows up there. It was capacitors, the way a capacitor discharges. Was described by that. E is a very interesting number. I actually have a book about E, but where it comes from. Pretty fascinating number. You guys ever heard of Fibonacci numbers? Fibonacci series? Fibonacci series goes like this. This is kind of like 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, dot, dot, dot. You see what the pattern is? Is that like the previous number? You get the next number? So like 1 plus 1 equals 2, 2 plus 1 equals 3, 3 plus 2 equals 5, 5 plus 3 equals 8. Yeah. So those are called Fibonacci numbers, and E has a very close relationship essentially with the Fibonacci sequence, Fibonacci So it's just a number that occurs in nature, and I'm going to today kind of prove to you how it shows up. Does that make sense? So let's do this. Here are some key ideas. If you see that the rate of change of y is proportional to the value of y, that's expressed by this equation right here. Think about that. Rate of change, that's derivative. Oops. Rate of change is derivative. Try that one more time. Rate of change is derivative equals ky will be proportional to y. So I should think about this. What are some things whose rate of growth is proportional to how many things are there? Just think of something just in nature, I guess. It might be real or it might be more fable than anything else. Population could be something. Population of what? Can you give me a specific animal?
Yeah, bacteria.
Birds, bacteria, what else?
Basically everything is at the point where you're increasing population, then that increases even more because different people have more children.
If there are more people having more kids, then the rates just increase.
Yeah.
So the classic statement is bunny rabbits, right? You know what I'm talking about? Bunny rabbits seem to repopulate very, very quickly. If you see a field of 10 bunny rabbits, when you come back a week later, there's like 200 of them. All over the place, right? Seems like it. I mean, if you live in, I don't know, like the edge of town, I'm sure you've seen that. So there is some realism to that, and then there's also some unrealism to that. I want you to think about this. If we were to graph the population of people, bunny rabbits, bacteria, whatever, an exponential curve, doesn't it do this? Right? So it's increasing forever. And the further to the right you go, doesn't it just keep getting steeper and steeper and steeper? Doesn't it seem a little unrealistic to you?
No.
What might limit the growth? Okay. Predators. I one time saw a bald eagle riding on a motorcycle. Saw a bald eagle, I kid you not, come from above and behind me, swoop down, kind of off to the left in front of me to this field, grab a prairie dog with its talons, go back up in the air, take off. It's awesome. It was like one of those nature shows. I was like, oh, dude, that's awesome. Blood and guts hanging off the prairie dog. You know, like, man, that's the coolest thing I've ever seen. Almost, I mean, I'm over speaking, but I felt like I was going to crash my motorcycle. Wasn't look. I mean, if somebody had walked in front of me at that moment, I would have just ran right over it. It was the coolest thing. So yeah, I mean, if you get a bunch of coyotes or eagles or whatever, and figure out that there's a bunch of bunnies in this field, population's going to change. Victoria suggested food. What about people? I mean, what might be some limiting factors for unlimited growth of population of people? Sure. Diseases. How about space? How about space? I mean, we live out west, and it just seems like if you want to have a bigger town, just make it bigger. But I don't know if you've ever been back east. I mean, some of those towns are really densely packed in. In fact, New York City is on a series of islands, right? So I mean, think about Manhattan. Like, how many more people really can you fit in Manhattan? I mean, you can keep moving the buildings up, but as far as land area, they've run out of land, unless they turn Central Park into a, like a village or something like that. And so, yes, space can be a big factor. So for that reason, typically for a population, what we're about to talk about doesn't fit very well. Okay?
It's sort of a factor. I mean, I guess if we're just considering population of the town.
What's sort of a factor? You said it's
Because there's all sorts of space. I mean, there's almost unlimited space.
if you move up.
Right. I guess in the city of Manhattan. I
Right.
mean, just in the world in general.
There is a limited space. I mean,
There is.
they say, this was several years ago, this is maybe like 10 years ago, so it's probably untrue now. But it was said that you could take every single person in the world give them 2 square feet of space, which isn't very much, and you could fit every single person in the city of Atlanta. Like just within that land area. And Atlanta's, you guys know what the biggest city in the US is in terms of land area? Jacksonville, Florida. At least that was true 5 years ago. I researched it again, but they just have a ton of land. It's nowhere near the biggest city population-wise. They just have a ton of land. And so we're talking about population density. So what would population density do to limit that? Right, yeah, but like along the lines of Manhattan, what if we just kept on making higher and higher buildings? Like, let's do some 200-story apartment buildings or something. I mean, there is, like, in a sense, sort of unlimited vertical space, isn't there? Kind of. But what would, that would make your population a lot more dense. You're fitting a lot more people into the same space. So what about that might ultimately limit your growth? Right, yeah, you could have the whole building fall apart, right? But besides some catastrophic event like that, what could happen? The population density would radically come down. We're all packed in together. We have less personal space. Perhaps, perhaps. Seems like disease would spread a lot faster. Yeah. And even practically speaking, accidents. You know, things, you get people packed in. I mean, seriously, when was the last time you had like an 18-car pileup in Bennett, Colorado? Which is one of those 10 cars up in the system. Never! If they have 18 cars and they're already in one time, it's a miracle. But you know, in a population, a dense population area like Denver, yeah, you could have that. And so, yeah, the more packed in we are, probably disease would spread faster, accidents would happen, be more violent crime, and you're going to see. And so, then wouldn't people not want to live there? People wouldn't want to live there. I think Valor itself is a kind of an interesting growth model as far as population. And if you think about the growth of the student body of Valor, like let's say that this is year 0 and this is year, is it 6 years? I think we're 6 years old. I think this is the 6 years. I thought we were 5 or let's just say the 6. I can get that. Population took off really fast at the start, didn't it? It did. So I think they started off here with like 150 kids or something like that. And then those first couple of years, like the population growth was very steep, very high rate. Last year we had like 770 kids, I want to say. This year we only have like 840, 850, so we didn't have like a gigantic jump in growth, did we? So what's happened is it's kind of flattened out a little bit. Why has it flattened out a little bit? It's like, can you picture another like 200 kids in these halls? It's hard enough as it is, right?
Or it's like a controlled population.
It sort of is. It's. I think it's naturally controlled, but it's also like artificially controlled too. Right. Like they said, hey, we're going to cap the class at this, but that of course is kind of governed by space and resources. And so I bring all this up because I want there to be a sense of realism to what you learn here. This curve right here is what we call a logistic curve. Logistic curve. And what that basically says is that populations of bunny rabbits, people, any kind of a population typically will follow a curve like this, where population growth will be very quick at the start, and then over time will kind of tail off a little bit, flatten out. It won't necessarily go down, but it'll tail off. It won't be as steep. And it's just limited by environmental factors, right? But I want you to look at this for a second. The first part of this curve looks very exponential. In fact, we could do something like this, couldn't we? Right? So this is exponential growth. So the red is what we're going to study. And there are some somewhat practical applications of this. For instance, bacteria really follows like almost an exponential growth through its life cycle. Right? And then there's also the other side to this is exponential decay. An exponential decay does something like this. And there's a really good application for exponential decay, and that's radioactivity, plutonium, uranium, that kind of stuff. By definition, that stuff decays. It puts off like the gamma rays. I'm not a computer physicist, so I don't know all the details, but I know the basic plot. And so that stuff, nuclear materials decay according to an exponential curve. So that's maybe a reason to study this. But I just want you guys to know, as far as population goes, logistic is the more realistic. And we don't study logistic in here unless we just have a lot of extra time. That is a BC topic. We can talk about that in quite a bit more detail, what the equation looks like, where it comes from, and all that stuff. So, or whatever that's worth. So here's what I want to do. I want to prove to you guys that E really works. Because you've seen this, right? You guys have seen this several times. And your teacher probably is like, hey, it's E. E naturally occurs, out there in the environment. And so this is the rule that we follow, right? And you're all like, okay, sounds good. So let's figure out where this comes from. Is that okay? So let's do this together. Let's look at the proof. And what we're going to do is we're going to start off with this. dy dt is equal to ky. So how do you make a connection between this thing that I'm boxing in red and drawing an arrow to what I just wrote? What's the connection? Is that the same thing? Looks kind of the same, kind of different?
It's the same thing, just you change y prime.
So why am I allowed to change y prime into dy dt?
Oh, I don't know what's prime.
Time, right?
Cool. Why does it have to be in time?
Yeah, why doesn't it? That's a great question. Yeah, as time passes, things change. So in other words, the growth and decay depends only on time, right? Now the rate of growth or the rate of decay also depends on that k value. Do you guys know what that k value is? It is a constant. That's a really important point. It's like 5 or 1.7.
Proportionality of the faster valuations.
How fast it's growing or how fast it's growing. Yeah. Sam, what were you going to say? Okay. So yeah, k is a constant. So just think of that as like 7. Okay. So we're going to do, we're going to take this differential equation, and we're going to solve it for the solution. Okay. So your first step is to separate the variables. Okay. So here's what that looks like. You separate the variables, you're going to get dy over y is equal to k dt. So what I essentially did there is I multiplied both sides by dt and divided both sides by y. So that means y left and dt right. All that okay? Okay. So once you've separated the variables, the next step is integration. Yep. So let's integrate both sides. And we know the integral of dy over y. Natural log. Yep. So natural log of y.
Where do you get that from?
1 over y.
Oh.
Same thing. Thanks for asking. So ln of y is equal to, what's the integral of k dt? Nice. It's kt plus c. Remember that k is a constant. So that would be like the integral of like 5 dt. Would be 5t plus c. So yeah, kt plus c. All right, we integrated. If we were, doing an AP test, we would have already earned a couple of points here by separating the variables, integrating, putting the plus c. We'd be on our way, doing pretty good. But we got to solve for y. We're going to get the y all by itself. How do you do that? Yeah, e to both sides. Very good. So e to both sides gives us y equals e to the kt plus c. Yeah, sure. Oh, my internet went out. Let me see it down there in the little orange thing. Pretty cool. It's the second time it's done that. Okay, so I'll just continue over. So when we compare that with where we want to go, it's pretty close, right? Because we want to get to y equals CE to the KT, and I've got my y by itself, I've got my KT, I've got my E, but the C kind of seems messed up, right? It doesn't look exactly the same. It's definitely different. Does anybody have any idea how you can kind of reconcile those two things? I'm going to let you stew over this for just a second. Right. Really?
Mess with your parents.
You got a question, the real practical purpose of that other than practical jokes. That's fun though. All right, we got to figure this out. And the other thing is if we differentiate, then we put derivatives back in there, which we don't want. So this is actually, strangely enough, this question is more related to algebra 1 than anything else. Think this through. How do I turn that e to the kt plus c into c e to the kt? Like, what's going on when you're adding your exponents? Because you see that the exponent is a sum, something plus something else. So how can we break that down to make it look more like what we want to do? You can separate them out. Really close. I'll even put this in. Times. But when you multiply your bases, then you're supposed to add your exponents. And so those exponents are a sum. That means in break it apart, you have to break it apart by multiplication. Make sense? Okay, so what's e to the c? Slowly constant. So y equals c e to the kt. What do you think? Is that good? Cool. All right, so let's talk about what these different parts mean. And I'll just use this little space over here to do that. I'll do it like this. So can anybody tell me what the T stands for? Okay, this is more science class right? Can anybody tell me what the Y stands for? Here's the output. What is it? So can I call that final amount? Like you said, it's like after a certain amount of time, so it's like at the end. How about the C? Starting amount, yeah, good. And what's the K? Yeah, it's your growth or decay factor. It tells you how fast something is growing or how fast something is growing. So let's answer that question that's kind of cut off there. How do we know whether one of these functions is describing growth or describing decay?
It's positive.
Yep. So if k is positive, what does that mean?
It's growth.
Growth. And of course, k is negative, it's decay. Okay, so like I said, that's kind of like science class-ish, but I think obviously it's good for you to be able to apply that, so there's a strong connection between math and science. Okay, let's take a look here. Some of our examples. Like number 2. Number 2 says the rate of change of p is proportional to v. Guys, that's the key step right there. We need to be able to look at that phrase right there, and we need to be able to interpret that into math correctly. So what does that look like if you interpret that into math?
P1 is equal to KP.
I'm going to write it a little bit differently, Andrew, but you are right.
Or dp over dp.
dp dt equals kp. Okay, so I have some, I think, good news for you. If we have dp dt equals kp, we just spent 5 to 10 minutes talking about how you go from that and then solving for the solution curve, right? The good news is those skills that we practiced are very good. They're very necessary and they're helpful. However, if you look at this question and you say, okay, dp dt is equal to kp, you need to write that down. You look at that and you're like, oh wait, I know what the solution is, and I don't have to do any work. I know that the solution is P equals C e to the kt, and if you can do that, you're good to go, okay? So if you can make that direct connection without showing those steps in between, it's one of those cases where I'm okay with it and the AP folks are okay with it. Make sense? So you can just jump from the differential equation straight to the solution, as long as you recognize the pattern. I think that those skills are good, and when we do differential equations in section 6.3, those skills we just practiced, you're going to need to go with it. There's no question about that. But for this particular type of thing, if you can just jump to the solution. Okay, so there's some things we can plug in, at least one thing. Does anybody know what, there's one thing we can just plug in just by reading.
5,000.
5,000 for what? No.
So P equals 5,000.
When? So what is T equaling 0? Starting amount. Yeah.
Oh.
So since C is your starting amount, now Andrew, you're right. You can plug a 5,000 in for P, but that would move you into 0.
Yeah.
That would enable you to solve for C, kind of.
Okay.
You have to be able to deal with K as well. I'm just thinking that if we can recognize that C is 5,000, that's going to save us a lot of time. Right? Initial amount is 5,000. Remember that C is the initial amount. You just plug it in. So what do we have to be able to make this kind of a functioning equation, something that will help us? Got to have the K value. So how do we figure out the K value?
So plugging everything in, so it'd be 4750 is equal to 5,000 times e to the k.
5,000 e to the 1K. Yeah. So in other words, you're plugging in 1 for T, 4750 in for P. Now let's go over the steps. Make sure you know how to do this. We want to find K. What will we do first?
4750 divided by 5,000.
Mike, are you okay?
Yeah, I was just,
Okay, so what's 4750 divided by 5,000?
0.95.
0.95? Okay. Wonderful. You're still trying to find K, and it's up there in the exponent. So what do we do? Wow, good. Okay, so then let's talk about what K is. Will somebody give me the first, like the 3 non-zero decimals for K?
Negative 0.05 and 4.
81.
What?
0.0581.
5.
0.051.
What's the one after the 1?
3.
0.3. Okay. So are you guys? This is going to be a moment of just like complete honesty here. Do you guys know how to use the store feature on your calculator?
Yeah.
Okay. Because you need to use that, or you need to write out the whole number. Let's talk about why. This is exponential growth or decay. So if you were to cut this, number off like what we just did right here, and then later on use that. That's what we're about to do. You're going to be off by a lot. Okay, you're going to be off by a ton. And so let me. Oh goodness, technology, right? Yes, I know air server's already running. Thank you. We're here at our equation with the K value in there. So we could say something like P is equal to 5,000 e to the negative 0.0513. But this time we want to figure out the value of P when T is 5. So instead of T, we just plug in 5. So you put a 5 right there in place of T. Next time you can calculate or figure it out. So take it that one last step. Let's make sure that you know how to use your calculator correctly. Should be good. So, anybody have an answer?
3868.905.
Agreement? Sweet. Well, let's do one more. This will set us up really good for tomorrow. Let's do number 3. So bacteria. Bacteria growing in a culture pretty decently follows exponential growth so let's try this. What differential equation would you write for that? Sure.
dv/dt
Good. All right, so I'm going to let you guys work on the rest of it. We have about 6 minutes left. I'll give you like 3 or 4 of those minutes to try to work through this one. We'll check it out. So what did you guys get for C? Yeah, C has to be 100, so B is equal to 100 e to the kt. How do you guys figure out k? It doesn't give the same kind of information, does it?
Well, sort of.
Sort of, yeah.
You know that B is 200 at 1 hour.
Agreed. Yeah, obviously 100 doubled is 200.
So then,
So then 2, right?
yeah, so then you do the natural log.
Yep.
And that's good.
1 of 2 is equal to k. Agreed. So then we've got B is equal to 100 e to the ln of 2, whatever that is, times time, right? So then what do we plug in for time? Because it says, how many will there be in an additional 0.5 hours? Say it again? 1.5, right. So I'm just going to replace the t with 1.5. All right, so did anybody figure it out yet? We 2.943. Is that right?
840.
843? 843. Okay. So, let's be honest about this. Practically speaking, probably the question should say round to the nearest bacteria, right? Because you can't really have 0.843 of a bacteria, I guess. I don't know. I'm not a biologist either. But, technically speaking, that's the number, 33.843. Should be good to go. All right. You guys got any thoughts? Moving along really well. Should be in good shape. Just a piece of encouragement for you guys. Coming up with our schedule, particularly